All right, so anyway, the problem has been fixed, right? If you go to watch any of the podcasts from this week now, they're old podcasts. They're not the podcasts I recorded, obviously, but they have sound. So if you missed a day or you need to review something other than yesterday's quiz, which was not on last semester's podcast, they're all up now, but they're, again, from last semester. It's pretty much the same thing, but okay, it's not exactly what you might have heard this week. All right, so we finished off yesterday and we watched the videos of kind of how kinetic energy can be used to do work. All right, and that is, in the brick breaking there, okay, with the guy that broke the 22 sidewalk blocks. All right, so what we want to look at now is kinetic energy, because we talked about potential energy yesterday. Okay, potential energy had to do with what three things? What three things could influence how much gravitational potential energy you had? Terry? No. That distance is one of the things that can affect work, which is probably what you're thinking. How high the object is, the mass of the object, and the acceleration due to gravity. Those are the three things that can affect how much gravitational potential energy you have. Now, obviously, for almost all of the questions that we will ever do, gravity is a fixed variable. Okay, it is always going to be 9.81 unless a question tells you otherwise, which I can't remember doing any time in recent memory. All right. Okay. Now, for work, okay, work can be affected by two things, or we use them to get work: force and distance. Okay. Now, quick definitions here. Work is a what? Transfer of energy or a change in energy. So anytime work is done, something is gaining energy, something's losing energy. Okay, there's a change. And energy is your ability to do what? Work. Okay, so those are the two that's the interchangeability of them. They're not truly interchangeable, but they are certainly related very closely to each other. All right, so any moving object's got kinetic energy. When a solid object moves, we consider that every particle it's made of goes the same way at the same time. All right, everybody with me there? Okay, so then we can consider it to just be one object. All right. The kinetic energy of such an object is often called mechanical kinetic energy. Right? We have to differentiate because there are two kinds of kinetic energy. There's mechanical kinetic energy, which has to do with moving objects, and then there is thermal kinetic energy, which has to do with the individual particles of the object moving because they have thermal energy. Everyone follow me there? Okay, you guys know about what absolute zero is, right? Okay, at absolute zero, all thermal kinetic movement stops. All right, everything is a solid at that point. There's no molecular movement of any kind, no particle movement of any kind. Okay, but that has to do again with the thermal kinetic energy. Is it possible for something at absolute zero to have mechanical kinetic energy? Yes, absolutely. All right, you think about like things like comets and things that are way out in like the Oort cloud or something like that, way out of reach of the sun. They are very close to or at absolute zero, but they're still moving. Okay, it's possible to have mechanical kinetic energy. The object as a whole moves, even if the particles within it aren't. Okay, does that sort of make sense? Okay. All right, so good example, the one we always use when we're talking about transfers and changes in energy, is a roller coaster. All right, when the roller coaster is up here, most roller coasters, with the exception of some of the newest ones like the Hulk and things like that, where you get shot out at the beginning, okay, you get towed to the top of the first hill. When you're getting towed, what is the roller coaster doing? Right, okay, the chain drive or whatever it is that's moving you, the conveyor, okay, is towing you up to the top. It's doing work, it's exerting a force over a distance, it's giving you mechanical gravitational potential energy. Is it also giving you some mechanical kinetic energy? Yeah, okay, you weren't moving before, you're moving now, so you have some kinetic, not very much. So when you get up to here, most of your energy is potential. You might have a little bit of kinetic. All right, now, any object that has either one or both of these is also said to have mechanical energy. And we'll talk more about that in a couple of days, but it's important to sort of recognize it now. Okay, work is a change in mechanical energy, right? We talked about the other yesterday where heat is a change in thermal energy. All right, As this roller coaster begins to move down this hill, what happens to these numbers? Exactly. The potential goes down, the kinetic goes up. Okay? The potential goes down because you're lower, and height is part of potential energy. But as you go lower, you go faster, so the kinetic energy goes up. Is the amount the potential goes down by equal to the amount the kinetic goes up by? It is. Okay? That's the law of conservation of energy. In a perfect system, okay, in a perfect system where there was no energy lost to friction or anything like that, okay, that's what we would be dealing with. The mechanical energy of the object wouldn't change, but its amount of potential and kinetic would. Is everybody okay with that? Okay, obviously in the real world, that's not the case. Okay, that's why the first hill in the real world is taller than all the others. Because if you made another hill taller than the first one, would you get there? Not without assistance, right? Because you lose energy to friction, it becomes sound and heat and all those other things, and you get, huh, oh, then the ride would probably get exciting because you would go backwards, at least partway until you got hung up somewhere in a dip. Right? That's why all roller coasters, their second hill, okay, is always lower than the first. If you've ever seen the Mindbender, that's the way it works at West Ed. Okay, it tells you the top of a very tall hill, which is probably, oh, let's say 10 meters taller than the second hill. Right, and then so you go through this first big loop, and then on the second hill you go through the two tight loops, and then you're a little bit lower again, and you go through the third loop, and then you do some spirals before you end up at the bottom. Okay, is that making sense? All right, what about down here? What would I have lots of down there? Kinetic energy. Is that also where I would probably be moving the fastest on that ride? Yes. Okay, because down there I have the smallest amount of height and the greatest amount of speed. Okay, now, even if molecules are not physically attached, so it's not a solid object, can a fluid still have mechanical kinetic energy? Absolutely. You ever been to the wave pool or the ocean? You get hit by a wave, does it knock you over? Yeah. Okay. Those particles might not be connected, but they have mass. Okay, and they're moving not so much as a group, but sort of as a group. Okay, so a fluid, whatever number of particles hit you, okay, you feel that. Right, and same with the wind. When the wind gets moving, a lot of those particles that maybe aren't physically connected are still moving in the same direction, and a lot of them hit you at one time, and they can, move you around a little bit. Okay, or in extreme cases, pick things up and throw them. Okay, like in a tornado or something like that. All right, so thermal energy is kinetic energy of individual molecules moving in a random pattern. Do we feel that? Sometimes. Okay, sometimes you'll feel that. If you're, let's say, standing next to something really hot, you'll feel the movement caused by that. Okay, you guys follow me there? Thermal kind of becomes kinetic at that point. But just sitting here in the room where the air is essentially still, you're still getting hit by particles all the time. Okay, but do we feel it? Thankfully, no, it would probably drive you insane. Okay, if you felt every time a particle of air hit you, okay, we'd go nuts. Okay, it would be like millions of mosquitoes biting you all at once, and that would be uncomfortable. So yeah, we don't notice them because they're all moving at different speeds. They're all moving in different directions. They're not all hitting us on the same side. It's just something we don't notice. Plus, each individual particle is so small, it has so little mass that, again, it can't really make any noticeable impression. But when you get all of those particles moving at the same time in wind, you do notice it. It's a lot more mass, and it's all the same way. All right, so for kinetic energy, this is the formula for calculating kinetic energy. Okay, 1/2 mv squared. So, does mass affect your kinetic energy? Yes. What about speed? Which one affects it more? Speed. How do you know? Because it's squared. Okay, kinetic energy and speed have an exponential relationship. A car moving at 20 kilometers per hour has 4 times as much kinetic energy as when it is moving at 10 kilometers per hour. Okay, is that considerable? What are the implications of that? Yes. What are the implications of having an exponential relationship for something, let's say that like this car that's got 4 times as much energy at 20 as it does at 10? You're not all driving yet, and I'm surprised they never teach you this in driver's ed because they really should. That means it will take you 4 times as far to stop. 10 kilometers an hour difference. 4 times the distance to stop. Okay? So I always do this because I have small children, and I think it's important that everybody knows just how this relationship works. Okay? Work is a change in energy. Agreed? Okay. If I want to stop, okay, I have to do work. Agreed? I have to change the energy of my car. What does that? The brakes. Okay? The brakes turn your kinetic energy into sound and heat, all right, through friction. So let's say, can someone just punch this in? 30 kilometers per hour divided by 3.6. So 30 over 3.6 for me. 30 over 3.6, not the other way. 8.3? Okay. All right, so here's what we're going to do. We're going to compare 2 vehicles in a playground zone or a school zone. All right. The first one is going to be moving at the speed limit. All right. So force times distance is the formula for work, and I need to change my kinetic energy from whatever I have at 30 kilometers per hour to what number? No, that's my speed. I want my kinetic energy to be what if I'm coming to a stop? 0. All right. So my change in energy is EF minus EI. You guys okay with what I'm doing so far? All right. So force times distance then is going to equal 1/2 times the mass of the car times the speed of the car squared minus, what do I, sorry, the other way. What do I want my final energy to be? 0, okay, minus this, right? Everybody okay with that? All right, my final energy I want to be 0, and this is how I would calculate my initial. So can I just say that since my braking force would be backwards, it would also be negative? Can I say that? Is that safe to assume? My acceleration is going to be backwards, right? So what I'm going to do is take this out of here just for simplification. All right, since they're both in the same direction, the negative isn't really important. Okay, now, let's say the mass of the car is 1,500 kilograms. Let's say the force exerted by the brakes is, I think on average, it's around 7,500 newtons, something like that. Okay, 7,500 newtons. And we said that my speed, 30 kilometers an hour meters per second, was 8.3 meters per second. Okay? So can I find out how far it will take me to stop? I know F, I know M, and I know V. Agreed? All right, so how do I get D by itself? Divide by F. All right, so the stopping distance of a car, this is an easy calculation, right? That's why I'm surprised they don't show it to you in driver's ed. Okay, it's an easy calculation. The distance that you need to stop, okay, 1/2 times the mass of the car, 1,500, times 8.3 squared, okay, over 7,500. Okay, so it takes almost 7 meters. Almost 7 meters to stop. Okay, and that would be under like absolutely ideal road conditions. Okay, where your brakes were 100% effective. Okay, which we know isn't always true. 7 meters to stop. Okay, that's what? All the way to the wall from where I was standing. Okay, doesn't seem like that far, but if there's a kid 3.5 meters away, it's a long way. Okay, so 7.5 meters, or 7 meters, sorry, 6.8 meters at that speed. Now, how fast do people usually drive in a playground zone or a school zone? Well, the speed limit's 30. I'm asking what do people normally drive? 40. Yeah, let's just say it's 40. It's only 10 kilometers an hour difference, right? Okay, it's only 10 kilometers an hour difference. So let's set this formula up. Okay, can someone just punch in quick what's 40 over 3.6? Okay, 11.11 meters per second, or meters per second, okay, over 7,500. So all the other numbers are the same. All I've changed is now I'm going 10 kilometers an hour faster. And we all do it, okay? In a 50 zone, we drive 60. On the highway, we drive at least 120, okay? We don't think about 10 kilometers an hour isn't very much. Oh, well, that won't work, okay. Okay, it's 1.5 times as far. It's actually almost 1 3/4 times as far. Okay, it almost doubles your stopping distance. 10 measly kilometers an hour nearly doubles how long it will take you to stop because you have exponentially more energy to get rid of. Okay, you guys follow me there? If you went 60 in a playground zone, it would take you 24 meters to stop. Actually, it would be more than that because it was 6.8, so multiply that by 4, that's actually almost 30 meters to stop. Okay, it makes a huge difference. How fast you're going makes a huge difference for how quickly you stop. All right, what's the other thing that would influence how quickly you would stop? The mass of your car. Okay, the bigger the vehicle you drive, the longer it's going to take you to stop. It's simple physics. You have more inertia if you are bigger. Okay, and you have more energy if you are bigger. All right, so if you're driving a Prius, well, okay, you're probably going to stop relatively fast because they're light. Okay, but if you drive, like a big, Cummins turbo diesel 3500, well, it's going to take you a little longer. Okay, because it's much more mass to bring to a stop. Okay, so something to think about. Real world application. Okay, that's why there's different speed limits in different parts of town. And that's also why they patrol the 30 kilometer an hour zones more than they patrol the 50 and 60 kilometer an hour zones. Okay, it's much more important. Stopping distance being enforced there is far more important. All right. All right, we're going to move on to some examples here. I want you to copy down this example. It's a work energy theorem example. Okay, give it a try, and then I'll go through it. So I have a rubber band, and it's stretched 0.85 meters by a force of 60 newtons. So if we're writing down givens, what two things were we just given? Force, because that's always measured in newtons, and distance. All right, so distance is 0.85 meters. Whoops. Okay, force was 60 newtons. At what speed would it propel a 0.125 kilogram ball when released? So I was told a mass. Okay, and we're asked to find speed. That's the question mark. All right. So I do work on this rubber band, and I put elastic potential energy into it. And there's a ball sitting in it. When I let it go, all that potential energy will do work on the ball. Agreed? Okay. Will it be the same amount of work that I did in stretching the rubber band? Yes. So is that the amount of kinetic energy the ball will have when it leaves the rubber band? Yes. Okay. Whatever work I do on the system is the amount of energy that system will have at any point thereafter. It will be the potential energy in the rubber band, it will be the work the rubber band can do on the ball, and it will thus be the kinetic energy of the ball at the end. That's the understanding part that has to be there. Okay, does everyone follow my logic on that? Okay, and again, we're living in the perfect utopian physical world here. Okay, there's no energy lost to anything else. There's not even any sound when the rubber band snaps. Okay, because all of those things would represent losses of energy. So we're saying it's all perfectly conserved. So does that mean then that work would be the work I do will be the change in energy of the ball? Yes. How much kinetic energy does the ball have when it is sitting in the rubber band? Zero. It is sitting, right? It has no speed. So its initial energy is 0. So work equals EF minus EI, which we said was 0. Do I need to bother subtracting 0? Question, Alicia? Yes. All right, so I'm going to take that part off, and now I'm going to say that the work I do on the rubber band is equal to the final kinetic energy of the ball. What's the formula for work? Force times distance. What's the formula for kinetic energy? No. 1/2 mv squared, right? Okay, I was asked to find V. I have force, distance, and mass. How do I get V by itself? Right, divide everything else over, right? Leave V where it is, divide everything else over. Then what? Do I want V or V squared? V, so what do I have to do to both sides? Right, I have to square root. All right, so there's my formula. The square root of FD over 1/2 of M will give me V. So when we plug in our numbers, that's going to be 60 newtons times 0.85 meters over 1/2 times 0.125 square rooted equals V. So, little tricky when entering this into the calculator. Got to be kind of careful with how we do things. You could bracket the whole thing, okay, and do it in one step. But I would say if you're not really comfortable with brackets, that you could do it this way. Piecemeal. 60 times 0.85 is this, 51. All right, I got to divide that by the bottom, 0.5 times 0.125, 816. Now I'll take the square root of that, and there's my answer. Okay, the speed of the ball will be 28.6 meters per second. Now, if you want to do it all in one step, looks kind of like this. So 0.5, actually I don't need the other bracket. Get rid of that. Not 0.5. 60 times 0.85 in bracket divided by in brackets 0.5 times 0.125 in bracket, done, 28.5, or 20.6, sorry. All right, either way will work, but if you're not comfortable or not sure you're going to remember to put all the brackets in the right place, it probably is better to do it piecemeal. Okay, does everyone follow how that worked? Okay, those are the kind of questions that you will see on quizzes and unit exams to do with kinetic energy and the work energy theorem. I could have asked a similar thing if I'd have said, if it was fired straight up in the air, how high would it go? Okay, so if I fired that thing straight up in the air at its maximum height, how fast is it going? Goes up and it accelerates downward, 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 downward. Before it starts to come back down, is it stopped? At its maximum height, it has how much kinetic energy? 0. Okay, so then the work done in stretching the rubber band downwards would be equal to the potential energy the ball would have at its highest point. Okay, do you follow me there? Because at that highest point, it doesn't have any motion. It isn't moving, it's just above the ground. And so it only has potential. So that's where, remember how I told you on the first day that a lot of people who are good at math struggle at physics? That's where. Because they can't see that, they can't see what's happening there. Okay, and they can't get to the math. Right? So it's really important that we, really visualize, or sometimes even draw, okay, a picture. I often see doodles, okay, in the physics section of the Science 10 exams. That's fine, because I do the same thing. Except most of the time I can't tell what my own doodle is, but okay, it's just awful because I can't draw. You guys have seen my drawings. Okay, but you get the idea. It is perfectly okay to draw pictures on there, especially if you're a visual person. All right, so this came out to 28.6 meters per second. All right, so that's one example. Let's try that one. Okay, so copy that one down and then give it a try. Okay, so what am I given in this question? I'm told the mass of the rock, 550 kilograms. I'm told that it's going from rest, okay, to 4 meters per second. Okay, and I'm told that all of this work is done over a 25-meter distance. All right. As soon as I see VI or any V is 0, what do I know about the kinetic energy at that point? If you're not moving, how much kinetic energy do you have? 0, okay? So that's always a good sign. If I see 0, I don't need that number. Okay? Because at that point, there isn't any of that kind of energy. It would be the same if you ever got one where the height was 0. Okay? You wouldn't need to calculate potential energy when the height is 0 because it doesn't have any. Everyone follow? Okay. Is work a change in energy? It is. Okay? So if work is a change in energy, and I know it doesn't have any energy to start with, is its final energy equal to the change in energy? Yes, because it goes from 0 to whatever. All right, so final minus initial would be whatever the final is. So I'm just going to put down then that force times distance, the formula for work, equals the formula for the kinetic energy of the rock at the end. Okay. Now, I'm trying to find F, so what do I have to do with D? Divide. All right, so the force is going to equal the kinetic energy divided by the distance over which the force is exerted. So 1/2 times 25 kilograms times, was it 25? 550. It's a light rock. I don't know why they're pushing that with a tractor. 550 kilograms times 4 squared, 4 meters per second. Okay, and then divide that by, it was 25 meters, right? That was where the 25 went in. Okay, so when I do that, I will get the force exerted by the tractor. So 0.5 times 550 times 16, which is 4 squared, okay, divided by 25. 176 newtons, that's a pretty puny tractor. You or I could easily exert 176 newtons of force by, well, doing anything, practically blowing on something, right, would exert that much force. Okay. To give you an example, if I stood on something, I would be exerting 700 and some newtons of force. Okay. Yeah, so that's a pretty puny tractor. I mean, if it took it 25 meters to accelerate something to 4 meters per second, it's not doing a very good job. Okay. Is that making sense, guys? Right? Again, this is what you're going to run into. These are the kind of questions that will be on your quizzes and on your unit exams. Right? Mathematically, is there anything really tough about this? No, again, it's a matter of, okay, I got to remember that when energy changes, work is being done, and I have to figure out what kind of energy I have to set the work equal to. Okay. All right, try this one. Okay, this one doesn't have to do with kinetic energy. This one involves lifting something. So, first thing we have to understand is that the energy of this question, at least at the beginning, initially, is 0. All right. What kind of energy does it have if it is 30 meters above the ground? Gravitational potential energy. Have I changed this by doing work? I have. All right. So in this case, work is again going to equal, okay, the change this time in the potential energy. All right, we're not speeding this thing up. We're just taking it from ground level to the 3rd floor and depositing it there. All right, so we got a 10 kilogram package. So we have force times distance. Okay, actually, we don't even have to do that. It just asks us how much work is done. So we don't even have to do the FD thing, do we? Can we just figure out how much the potential energy changes by? Absolutely. Okay, how much energy do you have on the ground? 0. All right, so I don't even have to write that in, right? Do I have to do EF minus EI if EI was 0? No. All right. So, will that give me the potential energy on the 3rd floor? Yes. So we are looking at 10 kilograms times 9.81 times 30 meters. (2,943 joules). Okay. Question. Whoops, sorry, to the 10th floor. My bad. How much am I changing the energy by, or how much am I changing the height by? Can I cheat? Okay, here's why I can cheat, just in case you don't understand what I did. M times G times H F minus M times G times HI. Do they both have mg in common? Can I eliminate it? Yes. Okay, I mean, if they have it in common, I only have to multiply by the difference in the heights. Okay, we could still go m times g times hf. That would be m times g times 100 and minus this, but we'll get the same answer. Agreed? Okay, so sorry, by 70. $6,867 joules. All right, Bill's going to go here right away. Reminders. Okay, you already handed in your graphing lab, but your need for speed lab is due December 3rd. I have had a bunch of you already submit it to me. Okay, and that's fine. I will try my best to have a look at it over the weekend, but I won't make any promises. If you come in on Monday into scheduled help, I will definitely go over it with you then. Okay. No. Oh, you weren't here yesterday when I changed my mind. Or yeah, I changed my mind yesterday. If you have it done, great. Hand it in. Right? It won't get lost in the box.